Welcome everyone to today's Ask the Experts presentation. I am Gail Eckert, Director of Marketing for Qualmark, and I'll be moderating today's event. Qualmark is pleased to be able to offer these free webinars to help keep you informed about accelerated stress testing and the many benefits HALT and HASS can bring to your reliability program. Please be sure to visit qualmark.com to learn more about how our technology and services can help you improve product reliability and reduce warranty costs. Qualmark Center of Excellence is hosting today's session on HASS fixturing and integration. This is the second webinar in a series focusing on HASS the Center has planned for this year. Experts joining us from the Center today to present are Neil Dortenbaugh and Chris LaPlante. Welcome, gentlemen.
Thank you, and thank you all for joining us today. This is Neil Dortenbaugh, and I'd like to start off by giving you just an overview of what we'll be covering. The first thing we want to get into is the information that you'll need to get HASS started. What you need to gather during the HALT test that is required beforehand, and go into some details there. Then we'll get into the fixturing, why it is different and what you have to think about as you're doing HASS. Altogether different tasks than the HALT fixturing. Then we'll step through the fixture development process, just from beginning to end, sort of a project plan for what it takes to get fixtures designed and HASS implemented. And finally, we have a lessons learned slide of some of the, just like in HALT, the best way you learn is by failing, right? So we'll show you some of the mistakes that you can avoid in our lessons learned section. So with that, I will turn it over to Chris, and he can lead us into the information required for HALT and HASS. Chris?
Thank you, Neil. As Neil said, before we get into the main topic of the presentation, I'd just like to review the information that you get from HALT and how it can assist in your HASS development. HALT must be performed before you can go into HASS. The data gathered is key for progressing in the reliability process. That's why maintaining a thorough report during HALT is very important. Operating destruct limits, failure modes, key performance indicators can all help in determining HASS profiles once you go into setting up for HASS. But that is not the only information you'll want from HALT. Based on the results from HALT, you'll be able to perform root cause and corrective actions, which can be taken to improve on the product. On top of all the actual data recorded, the setup of the test in HALT is also very important. Locations of measurement sensors like thermocouples and accelerometers, product orientation and configuration, functional test routines are all vital in recreating a test, as well as ensuring similar response when moving into HASS. And I probably should have moved over to this slide to say that. All right. During the HALT test, thermal and vibration stresses are applied to the product under test. Through this, you will be determining the actual limits of the product, both operating and destruct. As a result of the HALT and implementation of the corrective action, you will push the operating and destruct limits out as far as possible, thus achieving maximum robustness of your product. After you've gone through this process and are ready to move into HASS, the design margins you end up with will be used to help define that HASS profile. Here are some examples of descriptions of failures found during a typical HALT. Simply recording just the stress level of the failure is not enough information. You'll want every detail of the failure mode to record when you move forward. You'll want to be as specific as possible, as the examples listed here are. Information pertaining to what test and specific stress the failure occurred at, how the product failed, what data, functional test equipment may have gathered, and any other visual observations that were made are all very important. They are key components for performing root cause and corrective action, as well as guiding that functional test development for HASS. In HALT, you have the opportunity to explore the viability of possible key performance indicators for your product. The data shown here was just one of many parameters recorded for this particular product under test. But this parameter, which was IOs per second, was found to be a valid indicator of early failure in a product. During HALT, we found that the systems that showed early degradation during hot step in this parameter were also the same systems that failed first. Monitoring for these key performance indicators during the less severe HASS stresses can expand the effectiveness of the HASS functional test by detecting marginal units even if they're not forced to fail. In this particular example, if your HASS screen was limited to 70 or 80 degrees, a couple of these products up here, indicated by the blue and red lines, would not have failed. However, they would have indicated degradation in IOs per second, as you'll see in these dips in the blue and red lines, and that can help indicate marginal product and help find products that would fail first in the field. The thermal and vibration responses vary significantly on different locations of a product, even within a few centimeters. You want to record specific locations of the thermocouples and accelerometers with descriptions and plenty of photos for your report. In HASS, the product configuration and fixturing will be different, so the measurements on the product in HASS will help you understand the effect of these differences. In order to make that comparison accurate, you have to have good record on your measurement locations. Here shows an example of an accelerometer and a thermocouple. You'll want good angles and photos of every sensor in your report. The more photos, the better. Just make sure to label correctly what you see in a photo. Don't just assume the reviewer will know what's in that photo. Photos, again, also for product orientation and fixturing are very important. The orientation of this product will change the product response to the stresses. By knowing the changes in orientation from HALT to HASS, you can better understand the source of the differences in product response when implementing HASS. Functional testing performed during HALT is often custom and developed specifically for HALT. The effectiveness of and deficiencies in the functional test during HALT are important to know when you begin HASS functional test development. Some products contain technologies and subassemblies with known fixed thermal or vibration limits, for example, LCD screens or batteries. During HALT, these sensitive technologies are isolated either within or outside the system in order to stress the rest of the product as effectively as possible. The effect of these sensitive technologies in HASS must be considered during HASS development. The configuration of a product in HALT is often stripped down to subassembly level to ensure maximum stresses for the most effective HALT. However, this changes for HASS, where products are often screened as an upper-level assembly. Similar to product orientation, the change in configuration will affect the response. Understanding the change in configuration will help you understand and deal with the change in product response for HASS. Now I'll hand it over to Neil, and he can handle the main topic today of fixturing for HASS.
Thanks a lot, Chris. Proper fixturing, as we say here, is essential to a successful HASS screen. And here, just to outline some of the differences. If you're used to doing HALT, you know there's some general guidelines to follow, and it's relatively straightforward. Keep it simple. We don't worry about how the product's mounted in normal use. We're worried about mounting the product so that we get maximum transmission, and understand the table characteristics so that we don't dampen the table and reduce the drive into the product. When you get into HASS fixturing, you have a whole new set of things to be considered with. Number one, we've got the product, or the chamber rather, typically as full of product as we can get it. And you want to have consistent thermal and vibration stresses across that fixture, from slot to slot, across all locations on the table, and from test to test as units are removed and put back in, It needs to be consistent every time. We also have to consider the durability. They need to be able to withstand multiple cycles of a HASS screen between PM intervals. When you consider the abuse the product takes, the fixture gets beat up pretty bad. It needs to be easy to load and unload. The human factors become a significant consideration. Throughput time gets cramped if it's difficult to get stuff in and out, and also, of course, the issues of heavy lifting and the rest become a problem. And you don't want to, if there's any way to avoid it, using nuts and bolts in the load and unload process. That'll typically require torquing every time you put a product in, and you're better off without that if you can avoid it. You also need to worry about protecting the product under test. You hate to damage it while it's in there. And cable management becomes an issue when you have that many products going in. So let's carry through and talk a little bit about some of these characteristics. Think about the thermal specs for your fixture design. Typically, HASS fixture is done at lower thermal levels than HALT, or HASS is run at lower thermal levels than HALT. So the fixture doesn't have to withstand as high a temperature. This gives you some freedom in material choices. So some of the plastics, nylon can become a possibility, certainly Delrin and others. The ramp rates that you need to achieve on your product become a factor in the fixture design because you need to be sure that you are allowing adequate airflow around the product to get the ramp rates that you need. And variations in the product need to be considered as well. I mentioned the human factor specs, repetitive motion, heavy lifts, personal injury. You can consider things like fixtures that are completely removable so that the product is loaded into the fixture outside of the chamber, and then fixtures are swapped out when you load new product into the chamber, and that can be done often with a lift table or some other assistive device to avoid injuries from heavy lifts. And make sure that you're getting the vibration transmitted in that you want to get, and that you're able to get all the connections and anything needed for functional testing to your product. Those all get trickier when you have as many products as you can in the chamber, and you have it happening time and time again by production people rather than engineers that are taking their time and have time to burn in a HALT. Key thing, of course, is getting good vibration transmission to the product. That's the primary point of getting the fixture designed right. And to do that, you need to understand the table itself. Realize that our table is not rigid. It's flexible. It has its own modes, and here you see some diagrams of the three primary vibration modes of the table. We always recommend, if you're fixturing multiple product onto a single large table, that you fixture in quadrants, because as you can see from these graphics of the first three modes, we tend to have uniform quadrants. And if you fixture something heavy in the middle here, you can dampen out this main first oil can mode and reduce the total drive into the product. Think about your material characteristics that you're using in the fixture. Are they going to be able to move as the table moves and drive the shocks up into the product that are coming from the table? And consider the dampening effect of the structure of the fixture. Again, looking at differences between HALT and HASS fixturing, this is pretty typical for a HALT fixture, if this is what's necessary to get everything held down tightly. Some all-thread rod, some 80/20 extrusions, maybe even machinist clamps used. When you get into HASS, it becomes a whole different issue. And here you see, remember the power supplies that we saw being tested earlier laying flat on the table, and we were testing 4 at a time on the table. Now we're in a HASS configuration with those supplies. We've changed the orientation. We actually have pneumatic clamps that are clamping down on the individual products, so the entire clamping process is automated to ensure consistent clamping pressures. Once the fixture validation has determined what those clamping pressures need to be in order to get uniform vibration across the units themselves. And here you have a fixture being used on a flat table. This one is actually designed to be used in our QFusion. I'll have some pictures of that a little bit later, where you'll have 6 fixtures like this in the chamber. If you're dealing with one of our standard chambers that just has a single table in it, here's a fixture designed to fit into a quadrant, so you'd load 4 of these into the chamber, each one holding 5 power supplies with clamps here that are holding the devices down. It's very important that you monitor on the product. We say this in HALT a lot, and it's critical in HASS as well. Simply determining the set point in HALT that gives you the excitation that you need on the product, you can't transfer the set point directly. You have to be looking at the product to see how it's responding. And what we're seeing here is the product response. So at a particular point on the product, we look on a hard drive, PCB, heatsink, etc., and looked at the gRMS level that we were recording at each one of those points, 2 different tables, but the same gRMS level on the table. So as you move from model to model, from a 2.5 by 2.5 to a 4 by 4 table, you can have big differences in the response on the product. And in a situation like this, you'd be adjusting the drive so that you have the response that you want to see on the product. In the end, when you finish HALT and you have your operating and destruct limits, those limits need to be in terms of product measurements, not chamber set points. When you think of the materials that you're using for a fixture, if you've ever designed fixtures for electrodynamic shakers, you have to forget everything you learned, because this is very different. Typically, aluminum is what we want to use. It's got good heat transfer characteristics, good machining characteristics. It's light and suits the purpose nicely, but transmits the shocks well into the product. In HALT, we use a lot of the extruded aluminum shapes, the 80-20. Those are also valuable for HASS fixturing. It's very strong, and once you put something together, it stays put together even in a HASS situation. And it's relatively straightforward to go through and check and make sure that all the connections are still tight as part of a PM, and can speed up your fixture implementation. You can build just about anything out of that stuff. If you're using plastics, if you're going to high temperatures, Ultem is good. It's expensive, but it'll do the job. Otherwise, Delrin and Raydel are good choices in a HASS fixture, especially now for the contact with the product, the parts that are actually clamping onto the product. You don't want to have those be aluminum anymore. We're looking at a plastic for those surfaces so that you can protect the product and not scratch anything in the process. Nylon can work if you're not going too hot. It needs to be monitored some because it will tend to deform more than the other plastics described here. Another key factor to concern yourself with is cable routing. You will have lots of cables coming out and going to your test fixture, and it's not unusual in a HASS situation to be customizing outlet ports. You'll see here one that we've had customers drilled several holes in, and with matching holes in the padding the foam that's in behind that plug, so you can route the cables out neatly, and those stay permanently in the chamber, and the units inside then plug and unplug into those. But worry about exchange times with the cabling, making it so that it is not easy to get them mixed up. Make it as idiot-proof as you can when you have that many cables coming in and out. Keep everything labeled and marked. Put in those stress relief loops where applicable. You don't have a lot of excursion on the product when it's in HASS, a few centimeters at most, So you don't need to worry a whole lot about having lots of slack in the cable, but there's places where you need it, and you don't want to have cables coming unplugged or seeing undue stress. And keep in mind, as all of us in test know, that connectors are wear items, and particularly with the vibration that we're doing here, you need to keep an eye on those to determine replacement schedules so that you're not damaging pins on new products because of scratches in the sockets on your cables that you've been using in HASS. Here's another example from a customer site where they're doing HASS on power supply modules. Give you an idea of how they handled their cable management. They kept it all neat and clean, everything staying plugged in nicely, and all the cable routing done so that load and unload is easy. If we consider the functional testing, in HASS, functional testing by necessity is neater, cleaner, more organized, and more carefully thought out. Now you've got the racks of test equipment that you're used to seeing in a production facility. And you'll have, and this again, showing cable routing coming up into the products under test. So now you are using the lessons learned from HALT, and HALT really gives you a good opportunity to wring out your functional testing and see what does and doesn't work, what you should be monitoring, what kind of failures you see. If you're getting error messages that are meaningless, you need to get rid of those before you get into production so that there's no interpretation that needs to go on by the operator. And you've also had a chance to learn about those key performance indicators so you know what other parameters you're looking for as you get into your functional testing. Another example of a functional test rack at another facility, very straightforward. And this was again for power supply testing, where they had the capability to, if a supply failed, just switch that one out with individual breakers for each supply to protect each one from overload. And you don't have to worry about damage to the product, as I mentioned, making sure that you're using a Delrin or other material wherever you have contact with the product. Here you can see we've got a HASS fixture that actually puts some dimples in the product, and can't have something like that going out the door. And again, the concern about damaged connectors being an issue. So we need to keep an eye on those. Yeah, HASS is supposed to find the problems, not create them. When you're thinking about the functional testing, be sure that you've considered all the cabling and any specific performance criteria. One of the things, of course, we run into as we get into HASS is cable lengths will get long enough that you may have issues with signal integrity or voltage drop, and if that becomes an issue, you need to obviously work with some heavier wire perhaps. One thing you do also need to worry about in HASS is making sure you use Teflon coated wiring throughout. Avoid the PVC. It over time can't handle the heat, even the heat of a typical HASS cycle, and it outgasses formaldehyde and various other nasty things. So it's best to stick with Teflon coated wire for all your internal wiring. And just to give you an idea of some steps that had been gone through by a customer, here is fixturing for HASS. Power supply fixturing, it's okay, but it's not great. It is easy to load and unload, but we have inconsistent clamping pressures across here. If you look here, we have a clamp on this end and a clamp on this end of this bar, and that bar goes all the way across the products to clamp down. Now, if you've done this before, you probably will realize almost immediately that there's going to be a bow in this bar. You'll get clamping force on this corner and this corner, and the rest of them will not see that same clamping force. Indeed, with a setup like this, you might even see the ones in the middle starting to move out. So that distance is too much to span with a bar of that thickness and still get good clamping force across the units. And equal clamping force translates to equal vibration transmission. And cable management here is pretty ugly. You've got cables in your way while you're loading and unloading, and it can turn into a spider's nest. And again, this fixture is clearly a better replacement for that. You've got the unit standing up now, so this bar, which is also thicker, is shorter, and we do get uniform clamping across there. We have just enough room in here to allow for the airflow we needed. That was something you need to worry about when you start putting multiple units in a chamber is, am I going to get enough airflow through them to get the ramp rates I need on the product? So that's an important piece to keep in mind. And in this case, we could get them pretty close together and still get the ramp rates we needed to get. Now, one of the unique challenges that you can run into is designing a fixture when you have a product that is essentially a card cage with a bunch of cards plugged into it and a motherboard in the back. Often, a product that is in its final configuration like that, a motherboard with daughter boards plugged into it, if you try to test that product assembled, you'll find that you get very poor vibration transmission into the boards inside. The product isn't a very good vibration fixture. When you get into a situation like that, you'll design, one of the best ways to approach it is to design a fixture that is built to hold those assemblies just like they would be held in a product, except it's all a vibration fixture designed to transmit the vibration in well. So you're not actually testing the final product. You're testing all the boards that go into the final product and all the interconnects that go into the final product. But then when it comes out of HASS, you remove all the boards from the fixture and screw them into the unit. And I put this in just as an example for to understand why we say over and over again, you've got to monitor on the product when you're looking at thermal and vibration. If you think about it for a minute, if your failure modes are happening on the sub-assemblies inside of a product, on boards or other components, and you have a housing around that, that housing, the structure that is around the sub-assemblies, is a big mechanical filter and will change the vibration characteristics on the product itself. And to get an idea of that effect, if we take a power supply, like we've been looking at before, and I put a triax accelerometer here so that we could get some measurements both here on a heat sink and here, so we could, and these were places where failures had occurred. So we were seeing breaks on these leads as one of the failure modes. Then looking at vibration transmission into this heat sink is a good thing to look at when we're trying to get a valid measurement for the stress the product is seeing. Now, if I look at those and look at what is happening then on the table, on the fixture, and on the product case, I see that if you look over here, you'll see the gRMS numbers that were being recorded at this same set point. And here in relatively small print, you can see the locations of each of those. But we see from Z here and the tabletop here, big differences in the actual response. And here they're stacked up, the differences that you see between table, fixture, and case. So where do I say my vibration level is? If I know that I need to have 20 Gs in my HASS screen, where do I measure my 20 Gs? It makes a big difference. And of course, the right answer is this final PCA assembly, where the failures are occurring, is where you want to measure. When you move into HASS, you very often, unless you're running pretty light production levels, you have a chamber dedicated to HASS. So, because if you try to use the same chamber for HALT and HASS, then engineering has to fight with production for chamber time, and production always wins. So it's good to have dedicated chambers. And Qualmark has designed and released the first chamber designed specifically for HASS applications to maximize the number of units tested per square foot of floor space and to minimize the dollars per unit tested in utilities and in initial test equipment purchase. You can see here 6 separate tables. Each one can be loaded with a fixture, and here you see loading up with power supplies. Now, when you get into a situation like this where you've got, if I can put 10 power supplies on each one of these shelves, I've got 60 units that I'm testing. Cable management and the interface card locations can become tricky. So what we've done on this chamber is we've provided dedicated portholes for each one of those levels that can be customized for any size and location across the back, so you can actually mount interface cards directly to the back of the chamber and then take those off to the functional test equipment. So when you have a chamber full of product that looks like this, you can have cards mounted on the back here and keep your cable management neat and clean. As I promised, this might be a good one to take another look at on when after the webinar and you actually get into fixture development, because what we have here is a timeline of the key factors that happen during the fixture development, and this is based around a concept of this piece happening at Qualmark by the Center of Excellence for a customer, and then going on site to do these final components. And you can see that we start clear back from looking at customer requirements. What do we need to know for capacity and throughput? Go through some pre-development ideas, get into final development, do CAD, do some simulations to see how the fixture is going to respond. Then we'll actually get into the design qualification, making sure that not only does the fixture perform like we want it to, but that multiple fixtures in the chamber at once perform like we want them to. And then, once we get through this piece, we move to the production floor, and you have to do this again. You need to do fixture installation qualification once we get actually installed at the customer site. Is everything going to work? And then a system integration test. So we're plugging in functional test equipment. We're making sure that communications, if set up between the chamber and the functional test equipment, are performing like they should, so that the entire package is up and running and the people that are operating the chamber and installing units have had a chance to get their hands on the fixture, operate it, and determine what's right and what's wrong with the fixture from a true operator standpoint. All of this whole process is the skeleton for the project timeline and guidelines when you implement a HASS fixture in-house. Somewhat more significant than doing a HALT fixture. I usually try to get that done in the first half day of HALT work. The process for getting HASS done is more significant. We'll start off with the design review, making sure that everyone understands what we're doing and we've got an appropriate course of action for the fixture laid out. The validations I've discussed and verification, making sure we're meeting that design spec, which will include the stresses on the product, and as we mentioned, the same monitoring of the control points from HALT, so that you can make sure that this is a little vague, the same form of excitement. We're looking at the spectrums on the vibration and looking for gross deviations, and as well as looking at gRMS and looking at ramp rates and looking at how long dwells take to reach thermal equilibrium in that final HASS configuration versus HALT. We get all of this characterized as part of the validation and verification. The actual application, we'll sit down, figure out what you need to do for the HASS screen, do the proof of screen. Those are all topics for other webinars, but the creation of that screen is a critical piece of it. Make sure that what you're measuring on the product is look at how it's happened in HALT, how it's happening in HASS, document everything. In HALT it's critical, and in HASS it's critical. I often say HALT and HASS, you gain a huge amount by using these test methods, but there is an investment. And a key part of that investment is engineering involvement and paying attention to details, because you need to know so much in order to get it right. So keep your documentation straight and your records straight. Here's the lessons learned that I mentioned. And this is as true in HASS fixtures as it is in every other aspect of design work. Let's get the spec nailed down early so that it doesn't slow things down later. Stumbling in without a clear idea of where you want to get to can be dangerous. Make sure that you've got what you need to validate the HASS fixture. This is HASS fixture validation is the most intensive use of my spectrum analyzer. And you often need a whole lot of channels of thermal data in order to verify what's going on in HASS. Have that test plan laid out, understood, and agreed upon with all the people that are going to be involved. Get the resources planned. Don't let this implementation be an afterthought. As I say, it is an investment, and you need to have the manpower ready for that investment. If you don't have it, it'll slow everything down. And make sure you've got enough time to get it done right. When you find problems in HASS, they have to be paid attention to so that your startup is clean. So these are all things that we've found the hard way. So take our word for it. These pieces are critical. So that just about brings us to the end of the webinar. In summary, as Chris described, HALT is a prerequisite for HASS. You have to have that done, not only for the limit information, which is critical, but also, as we described, the KPI discovery. It gives you a chance to see what makes sense and what doesn't make sense to monitor, what works and what doesn't work in functional tests, and what sensitive components you may have and how they're reacting and what to do about it. I probably should have underlined this point and put it in red because it is critical. If you find issues in HALT that for some reason you decide, I probably don't need to worry about it, it's going to be expensive, let's wait and see if it's an issue in the field, I don't have time, I'm going to miss my window, all those other excuses for putting off a fix will bite you big time when you start HASS, because you'll have, if there is a distribution to that failure mode, it will be falling out in HASS in some significant fraction and not falling out in functional test because you need the stresses to make it happen, and you'll have arguments with manufacturing and production delays and all sorts of ugly things happening. If you've found something in HALT, make sure it gets fixed before you get into HASS. Keep in mind the implementation is different. It takes planning. It takes a lot of people involved. It's treated like a project, and you'll get it done right. And there's a lot of things to consider with fixture design, the table, the product, the potential for damage, the potential for damage to operators. All of that has to be concerned. And remember, you'll want a dedicated system, chosen to meet the throughput, space, and cost constraints. And at the end, keep in mind that Qualmark's Center of Excellence can help you at any point in a HASS implementation. We can go from being the equivalent of project managers on a project like this to simply being an advisor, designer of the test fixture, producer of the test fixture, advisor on test fixture design. Whatever level of support you need, we can help you so that your implementation is smooth and fast and starts saving you money as quickly as you can. So that's the sum total of what I've got to say right now. I'll let you take it back now, Gail.
Okay, great. Thank you, Neil and Chris. We do have a few questions coming in. One of them I think we hear frequently is, how do I know that HASS is not going to damage or reduce the life of my product?
Oh, yes, indeed. And I'm sure that this presentation was focusing on HASS fixturing, so we didn't get really into the HASS theory. But proof of screen is the key element that makes sure that your final screen is not going to take excessive life out of the product. And it's a very simple matter of designing the proposed screen. You show that it finds the failures you want, and then you run it 20 to 50 times on known good product and show that those products still pass test without any end-of-life failures after that many screens. So you can say with some confidence, and I think we have a paper on our website that goes into great lengths and a lot of words and numbers to say if you can go through 20 cycles with no end-of-life failures, then one cycle will take less than 1/20th of the life out of the product.
Okay, thank you. And I did have a question that came in actually during the HALT portion of this. What about thermocouple placement? Did you want to talk about any differences between HALT and HASS? And then what about triaxis placement?
Well, in HASS, you won't be monitoring the product at all thermally. There's no point in taping thermocouples on. It's the HASS during validation, fixture validation and screen validation. You'll have lots of thermocouples in there making sure everything's behaving the way you want it to. And you will want to be looking at, if I discover that I've got an upper temperature limit of 90 degrees and that upper temperature is measured on a circuit card inside the chamber, then that's where I want to be measuring when I get into HALT or into HASS. I've decided to guard band that 90 down to 70. That's where I needed to be measuring that 70 is at that same point. And accelerometers, same way. There's no point in trying to instrument the product during HASS, but you instrument it like crazy during HASS validation and the fixture validation. And triaxis are wonderful to use, and whenever I can, I put at least one on just so I have an idea of what's going on in X, Y, and Z. I don't strive to balance them, but I want to know what's going on so that I can see if they change between HALT and HASS configurations.
Okay, thank you. And what about the pros and cons of powered versus unpowered product testing?
Oh, that's right. When you talk about developing the screen, we talk some about the idea of precipitation and detection screens, where we'll run a first part unpowered and then turn the system on, reduce the stresses, and do a powered test. That's the only place where testing unpowered is acceptable in HASS as a universal opinion. If you simply stress it, then take it out and check it to see if you have any hard failures, you're going to miss a huge amount, and you're going to miss the expensive ones, the ones that only happen under stress but then go away when you take the stress away. And those turn into no defect found type of failures or intermittent failures in the customer's hands that are the most irritating and difficult to track down. So functional testing during HASS is critical. Being powered during HASS is critical. And we hit that pretty hard when we talk about setting up the actual HASS screen.
I would like to thank all of you for joining us today and to Chris and Neil for presenting. Qualmark Center of Excellence is the leading authority on HALT and HASS technology and applications. You can learn more about the Center and some of their projects at Qualmark's website. This is the group you definitely want to contact if you need assistance with your accelerated reliability. While you're on the website, you might want to look under our resources section. There we have white papers and articles and previously recorded webinars that are available through our library. Hope you'll go there and scope some of that information out. Qualmark has issued the definitive guidelines for both HALT and HASS. Those are available in our library as well as on special landing pages, qualmark.com/HALT guidelines or HASS guidelines, depending on which ones you're looking for. So we hope you take advantage of these materials we have made available for you. And we, again, thank you for participating today and hope to see you again next month. Thank you, everyone.